Okay, now we're going to look at graphing again, but we're going to look at situations where we might have asymptotes. And so having L'Hopital's rule to calculate limits of quotients will be very helpful. So now when we're doing the graphing, we're going to go through the same steps as we did before, but instead of just analyzing f of x by getting the domain and the x and y intercepts, we're going to now also find asymptotes, because that gives a lot of information about graphs. Then, same steps as before. We're going to go through f prime, figure out partition numbers, critical points, do a sign chart for f prime, figuring out intervals where f is increasing, decreasing, getting the maximums and minimums. Then we're going to look at f double prime like we did before and find the partition numbers there. Do a sign chart for f double prime. Remember, positive meant that it's concave upward, negative is concave downward, and get points of inflection, which is where it's changing concavity. Then we're going to sketch the graph. We'll put the asymptotes, the intercepts, maximums, minimums, and points of inflection on the graph and then sketch it. Okay, so the first step here, we want to look at the function itself, and I want to get its domain. So step one will be analyzing f. So analyzing f, the domain is everything that makes the y value real. And so in this case, it's everything but 1. So x not equal to 1, all real numbers but 1. So now x-intercepts. X-intercepts will be where the y value is 0. So we're going to have 0 equal to 2x over 1 minus x. The only way a fraction can be 0 is if the numerator is 0. So the numerator is 0 when x is 0. And then our y-intercept. Y-intercept will be where the x is 0. If you let x equal to 0 in the equation, you're going to have that the y, f of 0, is going to be 0 over 1, so we just get 0. So x and y-intercepts are both the same value. Okay, now let's look at the asymptotes. Now vertical asymptotes, remember how we found those? The vertical asymptotes were going to be where the denominator was 0 once you had the fraction reduced. If you look at this fraction, it's already reduced. There's nothing that would factor in the numerator. So it's already reduced, so we know we have a vertical asymptote at x equal 1. Now what we want to find out, though, is what's happening to the function around that vertical asymptote. What is the limit of this function, 2x over 1 minus x, as x approaches the 1 from the right side? Well, we know that if we plug in 1, we would get 2 over 0, which tells us it's going to be a vertical asymptote. A non-zero number over 0 is a vertical asymptote. Is it positive or negative? Pick a number bigger than 1 and plug it in. So if I put in like 1.1, I would end up with a positive number on top, but I would have a negative number on bottom. So this is going to be a negative number, so that tells me this limit's going to be negative infinity. So just knowing whether it's going to positive infinity or negative infinity is all we want. We know it's going to one or the other because it's a vertical asymptote. Then look at the limit as x approaches 1 from the right side. Actually, I'm saying them backwards, I think. From the left side, it's 2x over 1 minus x. Again, we already know it's going toward infinity or minus infinity because it's 2 over 0. But plug in a number a little smaller than 1, something like 0.9. The top will be positive, the bottom will be positive, so now it's going toward positive infinity. So that tells us it's going upward from the left side. Okay, so now the next thing is going to be the horizontal asymptotes. So to get the horizontal asymptotes, I'm going to take the limit. Now it's a rational function, so the left and the right horizontal asymptotes will be the same. It's going to the same number on either side, but it's a rational function. So just take the limit of this rational function as x approaches infinity. A horizontal asymptote is looking at x approaching infinity or minus infinity. So just do one or the other here. When you try to evaluate the top at infinity, you're going to get infinity. When you try to evaluate the bottom at infinity, you're going to get a negative infinity because that's what the function will be approaching. If you want to graph the two lines, you can, or you can just think, well, if I plug in bigger and bigger numbers for the x, the top's going to be getting bigger and bigger and the bottom's going to get bigger and bigger but negative. So this limit would have an indeterminate form of infinity over infinity. So I could apply L'Hopital's rule to it. So this would be the same thing as the limit of the derivative of the numerator, which is 2. The derivative of the denominator is -1. And now we're letting x approach infinity. We don't have an x anymore, so this answer is just a -2. It's just a constant. So our limit is -2. Now, if you want to get the horizontal asymptote by using some of the rules we did earlier, remember a horizontal asymptote, you could also look at the powers and see that the power on the top was 1, the power on the bottom was 1. So the horizontal asymptote will be the ratio of their coefficients, which is 2 over -1. It's the same thing. Or you can apply L'Hopital's rule, recognizing the top and the bottom both went to infinity. So this is your horizontal asymptote, y equal -2. Our vertical one's x equal to 1, and we actually know what these two limits are on each side, and we know our y-intercept and our x-intercept. Let's go ahead and put some of this on a graph. We have vertical asymptote at x equal 1. We have a y-intercept at 0 and an x-intercept at 0. That's the only x and y-intercept, so it can't cross the x-axis anywhere else. We have the, from the left, we had that the limit of this function was going to be positive infinity. So I know from the left of 1, approaching 1, this function has to be approaching positive infinity. Approaching 1 from the right side, it's approaching negative infinity. So I know it has to be going downward like this. Now, the horizontal asymptote's at -2. I need to get that on my graph also. So I kind of drew this a little too tall here because it's going to be approaching -2. So I've got 1, 2. This is what it's going to approach on the ends. Okay, so now the graph looks like I'm going to have a piece of it down here. It's got to be approaching negative infinity and approaching -2. And it looks like it's probably coming from up above, coming down toward the -2. It's not crossing the x-axis anywhere else if it's doing this. Now, what I need to do, though, is I need to check my maximums and minimums first, though, and see if I'm missing something in the graph. But I do have a lot of information just having those asymptotes and the intercepts. Okay, step 2 is going to be studying f prime. So looking at f prime, first I've got to get f prime. The derivative will just be using the quotient rule. It's going to be 1 minus x squared on the bottom. Start with 1 minus x times the derivative of the top, which is 2, minus the top times the derivative of the bottom, which is -1. So my derivative is going to be 2 minus 2x plus 2x. So I'm going to have 2 on the top over 1 minus x squared on the bottom. So now, I need to do a sign chart. I'm going to figure out what my critical points are. My critical points here, my partition numbers, are the places where the denominator is 0 or the numerator is 0. So x equal 1 is a partition number. Is it a critical point? Is the original function defined at x equal 1? It's not, because 1 was not in the domain. So this is not a critical point, so there won't be a maximum or minimum there, but it is the only place that the derivative might change signs. So I'm going to do my sign chart for f prime. I'm going to put just 1 on there, so I've got f prime, and I want to see what's going on with f. So now, plug in a test point. I'm going to pick 0 over here. I know f prime of 0 is going to equal to +2, and f prime of 2 is going to be equal to, now notice when I put 2 in the bottom, I'm going to have a -1, but I square it, so I'm going to also get +2. So I'm going to have plus signs here and plus signs over here, which what that tells me is that my original function f is increasing on the left of 1, and it's increasing to the right of 1. At 1, it's not anything. So there's no max or min at 1. It's not even a point there. So 1's not in the domain. Okay? So we have it increasing. So the general graph that we're thinking right now of this thing getting closer to -2 here and going up toward infinity, and the other graph I have, it looks pretty good. So this is consistent with that. So now let's look at the third step. We're going to look at f double prime. So find the derivative of the derivative. Now this one, I'm going to go ahead and rewrite this as 2 times 1 minus x to the negative 2. I'll do that because the top is just a constant, and that makes it a pretty easy way to get a derivative just using the generalized power rule. Otherwise, you could use the quotient rule, and that's a perfectly good way to do it also. So I'm going to have multiply the negative 2 in front, so I'm going to have negative 4, 1 minus x to 1 less power, so now negative 3, times the derivative of the inside, what's raised to the power, so negative 1. So my second derivative is going to be positive 4 over 1 minus x cubed. So now, my critical points and partition numbers. The partition numbers that I would have here, it's what makes the numerator of the denominator 0, or the original function even undefined, and that's just going to be, again, x equal to 1. So that's going to be the only number on my number line again for the second derivative. I'm looking at f double prime sign, and then I'm going to see what that means for f. So when I plug in a test point, I'll pick 0 on this side, f double prime of 0, plug it into the second derivative right here. I'm going to get a positive 4, and if I found f double prime of 2, I'm going to get a positive 4 again. So I've got it positive here, positive here. Oh, this is a cubed on the bottom. I didn't look at the cube on the bottom. Okay. This one, if you put in the 2, it's now negative 1 cubed. So that's going to be a negative 4. So that's negative. Okay, so what that tells me about my function f is that the plus signs for the second derivative mean that it's concave upward. And the negative signs for the second derivative means it's concave downward. And that point here in the middle, 1, now there isn't a point there though. If there was a point on the graph at x equal 1, we would have a point of inflection. But there's not a point there. So this can't be a point of inflection because there's no point. But it does change concavity. So if the original function was defined there, that would be a point of inflection. So our graph then, we showed that it was increasing to the left of 1 and increasing to the right, which is what we have already. And this one also says that it's concave upward to the left of 1 and concave downward to the right, which is exactly what we already have in this graph. That's exactly the way I drew it. So we have the graph. Okay. And so here's a picture of some of it, and there's some extra points that were calculated. So we have our domain, everything but 1, the y-intercept and the x-intercept were 0, horizontal asymptote y equal negative 1, vertical was x equal 1, increasing on this interval and this interval, concave upward on this interval, and concave downward on this interval. So we got all the information that was essential to get a good graph on this. Okay, now look at the graph of this one. Okay. First step, study the function itself. So we're going to see that there's an x in the bottom, so the domain is everything but x equal to 0. So x cannot be 0. The x-intercept is what you're going to get by setting the y equal to 0. So 4x plus 3 over x squared, but the only way a fraction is ever 0 is if the numerator is 0. So 4x plus 3 is 0. So x is negative 3/4. So that's our x-intercept. Okay. The y-intercept, let the x equal to 0. So h of 0 will be 3 over 0, which is undefined. There is no y-intercept. Okay. So now let's look at asymptotes. Horizontal asymptotes, that's when you're looking at the limit as x goes to infinity or minus infinity. And we've done this several ways. If you look at the limit as x goes to infinity of this function, you can first try to evaluate the top. You would get infinity. As x gets larger and larger, the numerator is going toward infinity. The bottom is also getting larger and larger, so this is actually an infinity over infinity indeterminate form. So you can use L'Hopital's rule, which says this is equal to the limit of just 4 over 2x as x goes to infinity. Now notice now we have 2 over x. As x gets larger and larger, the bottom is growing, but the top's staying just a number. So this limit is actually going towards 0. Now, if you remember, because the powers here on the numerator was 1 and the bottom was 2, the horizontal asymptote in those cases, when the power on the top was smaller than the power on the bottom, it was always 0. So we do have a horizontal asymptote of y equal to 0. Vertical asymptote. Now we know, because x can't be 0 here, and it doesn't reduce, that x equals 0 is going to be a vertical asymptote, but what we want to do is see what is happening on both sides of x equal to 0. So let's look at the limit of 4x plus 3 over x squared as x approaches 0 from the right side. We know it's infinity or minus infinity, because you would get 3 over 0, which is one of those cases where you have a vertical asymptote. If you plugged in something a little bigger than 0, like 1, we would have a positive number on top and on bottom, so this limit's actually going to go toward positive infinity. The limit as x approaches 0 from the left side. Again, we already know it's infinity or minus infinity, but if you plugged in a -1, you're going to get a -1 over a positive number. That's going to be a negative, so that's going to be a minus infinity. So we know which direction it's going, up or down, on the left and right of 0. So let me go ahead and get a graph started here. Okay, we know that the x equals 0 is our vertical asymptote. And our horizontal asymptote is actually y equals 0. Okay, and x-intercept's -3/4. That's the only place it crosses the x-axis. So I'm going to make that -1. So we have a point right here. That's the only. Now notice it's on an asymptote. It's okay to cross the horizontal asymptote. Horizontal asymptotes just tell you what's going on as x is getting larger and larger. It can cross it any number of times, for smaller values of x. It can never cross a vertical asymptote though. Okay, so now that's all we've got on our graph. It doesn't give us a whole lot. We do know to the right of 0 though that it has to be going toward positive infinity. So we know it's going up like this. And we know to the left of 0, it's going toward minus infinity. So we know it's going down like that. So I'm just going to draw that. I'm not going to jump the gun here and do the whole graph at the beginning like I did last time. Okay, so now step 2, let's look at the derivative. So f prime of x, I need use the quotient rule again. It's going to be x squared on the bottom. I'm going to move this down a little bit. Get my graphs away. So I'm going to have x squared, so x to the 4th on the bottom. I'll start with the x squared on the top times the derivative of the top minus the top, put this in parentheses, times the derivative of the bottom. So I'm going to have 4x squared minus 8x squared minus 6x. So I should have, let's see, that'll be a minus 4x squared minus 6x. Now notice there's a lot of x's floating around. Let's get rid of some of those. Take an x out of everything on the top. And I'm going to have minus 4x minus 6 on the top over x to the 4th. And that's just going to be minus 4x minus 6 over x cubed. Okay, so now my critical points and my partition numbers. Partition numbers are what makes the numerator 0, denominator 0, or where the original function was undefined. Well, bottom is 0 when x is 0, which is also where it was undefined. The top is 0, so negative 4x minus 6 is equal to 0, means that negative 4x is 6. And so that means x is negative 3/2. I went on and reduced it. So negative 3/2 is over here. Now, which of these might be critical points also? These are my partition numbers. 0 cannot be a critical point because the function was undefined there. So we have 0 and negative 3/2 are partition numbers. That's what we put on our number line. But the only critical point is negative 3/2. That's the only place we could have a maximum or minimum. So now let's look at what the derivative is. F prime And I don't need to put these partition numbers. We have them on our graph so you know what they are. F prime, we're looking for the sign of it, and then we're going to see what F is doing. Okay, picking a test point in each case. I'm going to pick -2, so I'm going to have F prime of -2. Put -2 into the derivative. We're going to have +8 minus 6 over -8. It's going to be a negative number, so it's negative here. I'm going to pick F prime of -1. If I pick -1 for the x's, I'm going to have a +4 minus 6 over -1. So it's going to be a positive number in there. And now pick something like 1. F prime of 1 is going to be -10 over +1. So it's going to be negative here. So what that tells me is that the function f is decreasing here, increasing between -3/2 and decreasing bigger than 0. So what's happening at -3/2 and 0? At -3/2, we have that the function was decreasing to the left and increasing to the right. So we have a local minimum at the point at f of -3/2. And we'll figure out what that value is in a minute. At 0, we do see it changing from increasing to decreasing, but there's not a point there. It's not in the domain. So we don't have a minimum or maximum there. F of -3/2, go back to your original function, put -3/2 for the x. I'm going to have 4 times -3/2, which is going to be -6 plus 3. So I'm going to have -3 on the top over 9/4. So that's going to be a -12/9, which is -4/3. That's the y value that goes with -3/2. So put the point -3/2, -4/3. So it's going to be down here. That is a local minimum. Okay. So now, what else is going on? We need to look at the second derivative. So we've got our local minimum. The second derivative, I'm running out of space. Okay, give us a little more space here. Second derivative, we'll need the derivative of the derivative. Our derivative, remember, was over here, minus 4x minus 6 over x cubed. So I'm going to use the quotient rule this time. It's going to be x cubed squared, so I'm going to have x to the 6th on the bottom. I'll start with the x cubed on the top times the derivative of the top, which is -4, minus the top, -4x minus 6, times the derivative of the bottom, which is 3x squared. Now I'm going to have a lot of x's floating around. I've got at least 2 extras on everything in the top, because I've got the x cubed and I've got everything times x squared on the second. So I'm going to factor out the x squared. Well, let me go ahead and just multiply it out. I don't want to lose you. Minus 4x cubed. I'll have plus 12x cubed. And then I'll have plus 18x squared. And all that's over x to the 6th. So now when I add like terms, I'm going to have 8x cubed plus 18x squared all over x to the 6th. Take out an x squared out of everything on the top, and you're going to end up with 8x plus 18 over x to the 4th. That's your second derivative. Okay, so now set up your number line. We're going to put 0 on the number line. What makes the numerator 0? So when you look at 8x plus 18 equal to 0, so x is going to equal to -18 over 8, which is -9 over 4. So we're going to put a -9/4 on the number line. Whoops, I just extended that out. -9/4. Okay, so that's what makes the numerator 0. 0 made the denominator 0. And now I'm going to pick test points and plug them into the second derivative. So if I pick f double prime of negative 3, I'm going to get negative 24 plus 18, so I'll have negative 6 over a positive number. So negative 6 over 81, which is going to be a negative number. All I care about is the sign. Now pick something like negative 1. F double prime of negative 1 will be negative 8 plus 18. So it's going to be positive on the top and positive on the bottom. So it's positive in the middle. And then F double prime of 1 is going to be positive on the top and positive on the bottom. So it's going to be positive over there. So what's happening then is that we have the functions concave downward from minus infinity to minus 9/4. And it's concave upward from minus 9/4 to 0 and from 0 to infinity. Now I can't combine those into one because 0, the function doesn't exist at 0. Okay, now is there a point of inflection? The only place the concavity is changing is at negative 9/4, and that is a valid point on the graph. So we have a point of inflection at negative 9/4, comma, whatever the y value is. So you have to go back to the original function and get the y value there. So let's see if I can go back and see what that is. Okay. So negative 9/4. So f of negative 9/4 will be negative 9 times 4 will be negative 9 plus 3. So negative 6 on the top. And then we're going to have a 81/16 on the bottom. So when we invert it, we're going to get negative 96 over 81, which does reduce. We'll be able to divide everything by 3. So negative 32 over 27, and that does not reduce. So this point of inflection will be negative 9/4, negative 32 over 27. So we'll put that on the graph. Okay. So negative 2 1/4, negative a little bit over negative 1. Now, how does that compare to that other number? The other one we got was negative 4/3. Well, that was the lowest point, so this has to be a little higher. So it's going to be a little bit higher right here. This will be negative 9/4, negative 32 over 27. And this first one was negative 3/2. It's right here. Negative 3/2, negative 4/3. Okay, so we've got those points on the graph. Now let's see what's happening with the graph. We're told that it was increasing or decreasing to start with. So it's got to be decreasing until it gets to negative 3/2. So it's coming all the way down until it's getting to negative 3/2. Okay. At negative 3/2, it's going to start going up. It's got to get to that point. And then at it keeps going up until it gets to x equals 0. Okay, so it's got to be increasing here. We got that it was increasing from negative 3/2 to 0. So it's got to be going up, continue going up until it gets to 0. Now that seems to contradict something we found earlier when we found that the vertical asymptote from the left side was negative infinity. So this will bring up a good thing that you'll need to check. Now, if we were looking at x approaches 0 from the left side, we plugged in negative 1 and got that that value was negative, and so it had to be negative infinity. But what you have to be careful of is don't get too far away from 0. When we picked negative 1 for the x, we were too far away. We need to pick something closer. Actually, if we were anything further away than negative 3/4, we were going to be too far away. So let's pick negative 0.1. If you put negative 0.1 into this fraction right here, you're going to have a negative 0.4 plus 3. That's positive over a positive. So when you're really close to 0, it's actually going to be going toward positive infinity. So we caught that mistake by checking the increasing and decreasing aspect of it. So don't get too far away from the x. Okay, so we have that the function's coming down, and then it's going up until it gets to 1, and then it's going to be coming down after that. It's from 0 to infinity. Okay, now the concavity in here, so now it's coming down, but notice the horizontal asymptote is 0. So the function's going to be coming down from 0. It's not going to go up above the x-axis, or we'd have another x-intercept. The only x-intercept we got was at negative 3/4. So don't go above the x-axis there. Now let's check the concavity before we've got something like this. It's coming down to here, it's going up from there on, and then it's going to be coming down all the time there. So now I'm going to get rid of this piece here. That's not going to be the case. And now let's get the concavity in there. We know that it's concave downward from minus infinity to minus 9/4. So until it gets to this point of inflection here, that's the point of inflection, it's going to be curved downward. It's concave downward. So we need it to be kind of curving down like this, but it's still rising, toward the left. And now at negative 9/4 on, it's going to be concave upward. So from negative 9/4 to 0, we want it to be concave upward. So it's going to be going like this all the way until it gets to 0. And we know it has that horizontal asymptote, that vertical asymptote there. And now from 0 to infinity, it's also concave upward that entire time. So this graph goes up toward that vertical asymptote, and it goes toward the horizontal asymptote as x goes to infinity. So that's what the graph is going to look like. And this is a mess because I didn't have a whole lot of room here. But let's go ahead and see what the picture looks like on the next slide. And you can see there, we did find that local minimum here. We did find the horizontal and vertical asymptotes. Just be real careful when you're figuring out what the y value is approaching near those vertical asymptotes. Stay as close to it as you can. And I believe all this information is what we got our x-intercept. We have our point of inflection here. We had our minimum. The local minimum was at x equal 1.5, and then we got all the concavity correct and all the increasing, decreasing correct. Okay, we're going to do one more of these. This one will have some of the exponential function in with it. It's the same steps, though. So the first thing I want to do is I want to look at the function. I want to figure out if there's x-intercepts, y-intercepts, the domain. This function I'm going to rewrite first as x over e to the 0.5x. Okay, now I can see what the numerator and denominator really look like. The domain is everything as long as the denominator is not 0. E to a power is never 0. If you think of the graph of e to the x, it's never 0. So the denominator is never 0. So the domain is all real numbers. And I'll say since e to the x is never equal to 0, there's no x that would ever make that 0. The x-intercept, it's going to be where the y is 0, which is going to happen when x is 0. And then the y-intercept is going to be when the x is 0, and we're going to have 0 over 1, so it'll be y equals 0. So same point there for the intercepts. The asymptotes, let's look at a horizontal asymptote first. Horizontal asymptote, see now this one's not a rational function, so you can't use your previous rules about powers of x. Horizontal asymptote is always the limit as x approaches infinity. So it's going to be x over e to the 0.5x. Well, if we try to evaluate this, we'd have infinity on the top and we'd have infinity on the bottom. So this is an infinity over infinity indeterminate case. So it's an indeterminate form. So we can take the derivative of the top and the bottom by L'Hopital's rule. So it'd be 1 over 0.5 e to the 0.5x. Remember, the derivative of e to the 0.5x is e to the 0.5x times the derivative of the exponent. The exponent. So now we have this. Now if you evaluated this, as x gets larger and larger, the bottom is getting larger and larger, and 1 is going to be almost nothing, so it's going towards 0. So our horizontal asymptote is at y equal to 0. Now, sometimes these exponential functions actually have different horizontal asymptotes on the two ends. Toward minus infinity here, but we'll come back and look at that later if we need to. Vertical asymptote. The denominator is never zero, so there are no vertical asymptotes. Okay, well, that's a lot shorter. So now that was analyzing the function itself. The next step will be looking at the derivative, f prime of x. Well, the derivative we can do by the quotient or the product rule, depending on which way you start with it. Let's go ahead and just write it as e to the 0.5x squared on the bottom. I'm just going to use the quotient rule. And then I'm going to have e to the 0.5x times the derivative of the top, which is 1, minus x times the derivative of the bottom, which is e to the 0.5x times 0.5. Okay, so I'm going to have e to the 0.5x minus .5 x e to the 0.5x. Now, I've got all these e to the 0.5x's floating around. I'm just going to leave the bottom as that squared right now. I'm going to factor an e to the 0.5x out of the numerator. And I'm going to have e to the 0.5x times 1 minus 0.5x. And so now one of the e to the 5x's on the bottom will cancel with the one on the top. So I'm going to have 1 minus 0.5x over e to the 0.5x. Okay, so the denominator is never 0 again. The numerator will be 0. F prime will be 0. You're going to get your critical points when 1 minus 0.5x is 0, which means that 1 is 0.5x, which that's just 1/2. That means x is equal to 2. So that's your critical point in your partition number. So when I do my number line for my f prime, I'm just going to put 2 on the number line. So I'm going to have f prime, and then we're going to see what's happening with f. And our derivative here, f prime, was equal to 1 minus 0.5x over e to the 0.5x. Okay, so now plugging in a number smaller than 2, I'll plug in 1 to the derivative. When f prime is 1, and when 1 is plugged into f prime, I'm going to get positive on the top and positive on the bottom. So I'll have a positive number here. When x is bigger than 2, something like 3, so f prime of 3, we're going to have 1 minus 3/2 on the top, so it's going to be negative. So negative on top and a positive on bottom, so we're going to get a negative here. So what that tells me then is that f is increasing from minus infinity to 2 and decreasing from 2 to infinity. Do we have a critical, a maximum or minimum at 2? Well, 2 is in the domain, and there is a sign change. The function was going up, and then it's coming down. So we have a maximum, local maximum at 2, and we need to know the y value. Plug 2 into the original function, and you get 2 over e. Because it's going to be e to the first power when you multiply it by 2. So 2 over e, that's 2 over 2.7, so it's going to be approximately a third, around a third. Okay, so we have a local maximum here, and we also know where it's increasing and decreasing. Okay, so now let's look at the second derivative. Step 3. The second derivative, using the same rule, we're going to do e to the 0.5x squared, the denominator, using the quotient rule. E to the 0.5x times the derivative of the top, which is negative 0.5, minus the top, 1 minus 0.5x, times the derivative of the bottom, which would be 0.5 times e to the 0.5x. Now I'm just going to go ahead and cancel out the e to the 0.5x. I have to take it out of everything on the top first, and it's going to end up being, I'll have negative 0.5 minus a 0.5 plus a 0.25x. Well, I've got to distribute this 0.5 through and distribute the minus sign through. So then I'm going to have all that over e to the 0.5x when I cancel the top one out. So I'm going to have -1 plus 0.25x all over e to the 0.5x. So the places I'll put my partition numbers here will be what makes the numerator 0. So set f double prime equal to 0. So we're going to have -1 plus 0.25x. When you solve this, take 1 to the other side, you're going to get that x is equal to 4. Because 0.25 is just 1/4. Okay, so now setting your number line up. We're going to have 4 on the number line. You're going to plug in numbers smaller, so I'll plug in 0 into the second derivative. So I'm just going to say f double prime of 0 is going to give me a negative number. So this is f double prime, and then we'll see what f's doing. Plug in something like 5, the top's going to be positive now, and the bottom will be positive. So we see that it's concave downward from -infinity to 4, and concave upward from 4 to infinity. At 4, we do have a point of inflection. So it's going to be the point 4, comma, and then whatever the y value is, which will be 4 over e squared. Okay, so now, trying to put this all together. I'm going to come back up here at the top. It's the only space I have left. Okay, putting my points, I only have x. I don't have any vertical asymptotes. I have an x and y intercept is here. I have a horizontal asymptote is y equals 0, so I know it's approaching this line. I have that the function, the maximum is at 2/3 approximately, so it's going to be right about here. And I have a point of inflection at 4 over, around 9, so 4.5. So it should be something like, that was a local maximum, so that was the highest point. So something like that is your point of inflection. And here's your maximum. Okay, so I have that the function's increasing from -infinity to 2. So it's got to be coming up all the way until it gets to 2. Okay, so it's increasing all the way until it gets to 2. So it's got to be coming up all the way until it gets to this high point here, and then it's going to be coming down from then on. And we know it has a horizontal asymptote to the right at least. We just looked at horizontal asymptotes as x went to infinity, and we know over here it's got to be going to 0. That doesn't appear the case now on the left. So let's go back and see what would the horizontal asymptote on the left side be. Exponential functions don't always have the same ones. So I'm going to look at the limit as x approaches -infinity of this function, x over e to the 0.5x. Now notice if you put in -infinity into the numerator, put in a big negative number, it's going toward -infinity. The bottom, though, as x approaches -infinity, that's a negative number now. That's actually going to be approaching 0. So let's look at that a little closer. Because we're plugging in negative numbers, we're going to have a negative exponent on the e. And I want to look at that as, let's change this to x e to the -0.5x. Because if we plug negative numbers in for the x, then this exponent then will become a big positive number. So as x goes toward -infinity, this is going to be a negative number, and this is going to be e to a big positive number, which is going toward infinity. So we've got an infinity times an infinity. It's actually going to be a negative, though, because it's this first term here would be negative. So the function is actually doesn't have a horizontal asymptote on the left side, only on the right. And so we do have this function. This graph does fit with what this limit is telling us for the asymptote on the left side. So now, let's get the concavity in there and then just quit. From -infinity to 4, it's concave downward. So I've got to have this whole thing until it gets to this point here, concave downward. So I'm going to have it coming like this. It's got to go up to there. It's going to come down to this point of inflection here. The whole time it's concave downward. So make sure you draw it so that it's curved downward. And then from 4 on, it's concave upward, but it is still going toward the horizontal asymptote x equal to 0, y equal to 0. So it's going to then just start going like that. So let's see if we have a better picture. I'm sure we do on the next slide. And this is what the graph looks like. We found all those details there. We probably went into the horizontal asymptote a little more than what, they said here it's at y equals 0. It's only on that one side that it's y equals 0. But that comes out when you look at the increase and decrease, and you figured that out. So that's all the information, and I think that's enough for now.